Hi, I'm Jahangirova. I work as a postdoctoral researcher at USE in Lugano, Switzerland, and I'm going to present our paper, an empirical evaluation of mutation operators for deep learning systems, which is a joint work with my colleague Paolo Tonella. So for traditional software systems, mutation testing is an approach where we take the original program, which is in this example is this method that does some sort of calculation, and we apply syntactic changes to it. So we change plus to minus, 3 to 4, mode of division to multiplication, and we get this set of programs with injected faults that are called mutants. Once we have generated the mutants, we take the test suite, execute it over the original program and each of the mutants. If this test suite contains a test case, the outcome of which is different for the mutant than for the original, then we say that this mutant is killed. If there is no such test case, then the mutant is not killed. The capability of the test suite to kill as many mutants as possible is an indicator of its quality. Unlike traditional software systems, deep learning systems, their logic is not implemented only in their source code, but it's rather scattered across different components such as training data, the model structure, hyperparameters that have been used for the training process. And once the training process is complete, we get a trained model that has weights and biases. So if we want to change the behavior of a DL system, then we have to either alter the training data, model structure, hyperparameters, or weights and biases of an already trained model. So these characteristics of deep learning systems has been already recognized by researchers, and there are two works, Deep Mutation and MUNN, that propose mutation operators specific to deep learning systems and provide their preliminary evaluation. Due to time limitation, I cannot go through each mutation operator and explain how it works. So the brief summarization would be that combined, these two papers propose 19 mutation operators. 7 of them are pre-training operators, which means that the change is applied to the deep learning model before it has been trained. So in order to get the mutated model, we have to retrain this model. An example of such a mutation operator would be label error. So let's say our training data consists of digit images and they have been assigned labels. We change the correct label to the incorrect one and we retrain the DL system. Another mutation operator that is a pre-training one is remove data. So let's assume for simplicity that our training set consists of these 4 images, then the remove data would remove a portion of this data and retrain the system. The remaining 12 post-training operators are applied after the model has been trained. An example of such an operator would be change weight. So let's say the model has been trained and this connection has a weight of 0.5, we change it to 0.75. There is a group of mutation operators which can be applied both before and after training. And the first example of that is remove layer, which removes the layer from the model structure. And the second one is add layer, which adds the layer to the model structure. So along with the propositions of mutation operators for DL systems, these two works also provide some definitions regarding the metrics of mutation killing. So actually in UNN, the authors do not provide any formal definition, but they use the accuracy of the mutant and accuracy of the original and check if the accuracy of the mutant has dropped. However, they do not provide like a threshold value, such that if the accuracy drop is greater than this threshold, then the mutant is considered killed. Deep Mutation provides 2 metrics that are specific to classification systems. The average error rate is based on the definition of error rate, which is the number of test inputs from the test set that get misclassified by a given mutation. The mutation score definition in Deep Mutation is based on the notion of killed classes. So if we have a classification problem, then let's say we have k classes of input data. The test input is set to kill a class If this test input gets correctly classified as belonging to this class by the original model and gets misclassified into other class by the mutation. So in this formula, they calculate how many classes does the overall test set kill for each mutant, and they sum these numbers for the mutants and divide them by the multiplication of overall number of mutants and overall number of classes in the classification problem. So these three metrics that I've been describing have some limitations. First of all, if we have an instance of a mutant, none of these metrics is going to tell you if the mutant has been killed or not. Moreover, these metrics do not take into account the non-deterministic nature of deep learning systems. But if we have a deep learning model, and even if we train it without making any changes, we can see that there is a slight change in accuracy once it got retrained. Moreover, the mutation operators, they change some parts, let's say, of training data. And if they change a different part of training data, at each of their executions, the outcome of each run of a mutation would be different. So taking account these limitations, we propose a statistical definition of mutation killing. And the prerequisite for the application of this definition is that a given mutation operator with a given parameter should be applied multiple times, and the original model should be retrained the number of times we want to apply the mutant. So let's say we want to do n runs of a mutant, then we retrain our original model and get n performance metrics for each of these runs. Then we get the same number of performance metrics for each mutation. And now that we have two sets, our definition says that the mutation is killed if these two sets, the difference between them is statistically significant, so p-value is less than 0.05, and the effect size is not negligible, so it's greater or equal to 0.2. If these two conditions hold, then mutation is killed. If they do not, then the mutation is considered not killed. Of course, different tests can be used for statistical significance and effect size, but in our experiments, we have used generalized linear models for statistical significance and Cohen's d for effect size, and we have applied 20 reruns for each mutation operator. So another distinctive feature of mutation operators for deep learning systems is that they require a parameter when we apply them to deep learning models. So let's say you want to apply the remove data operator to your training data. Then you will have a question of how much of this data should I remove? Should it be half of it, more, less? So the answer to this question is passed to the mutation operator as a parameter, which is called percentage of affected training data. And in the original paper, Deep Mutation, the value of this parameter was fixed to 1%, which means that we don't know how these operators change their behavior once they are passed different parameters. And to account for this, in our experiment, we have considered a large set of values in the range from 5 to 100, ensuring that the values are fine-grained in this range. Another example of a mutation operator that requires a parameter is remove layer. So if we want to apply this mutation operator, we might think, which of the layers should I delete? And again, here the parameter is the layer number. And in our experiments, we have considered values for such mutation operator in an exhaustive way. So we have, for example, removed all possible layers for a given deep learning model. So to conduct our experiments, we have picked subject data sets and systems. So we have picked two models for MNIST and two models for CIFAR, and both of them are classification problems. And we have one example of a regression problem, which is a DAVE2 model for Udacity self-driving car challenge. And the objective of deep learning model here is to predict the steering angle given the camera images of the road. So by applying all 19 mutation operators with the parameters as I mentioned in the previous slide, we have obtained around 16,000 pre-training mutants and around 7,500 post-training mutants. As pre-training mutants require the DL system to be retrained each time, our experimental procedure is quite expensive, and we were able to conduct experiments of this magnitude thanks to the Amazon Research Award that we have got for this project. So our very first research question focuses on evaluation of mutation operators on the basis of two characteristics. The first one is if the mutation operator is killable, and by that we mean that there exists at least one parameter for this operator that gets killed. To do the analysis to answer to this question, we use the largest test suite available for a given data set, and then we applied all the parameters to the mutation operator and checked if there is at least one killable. And out of 19 operators, for 3 of them, we see that no matter which operator we pass, it never gets killed. The first such operator is shuffling training data before training. The second one is duplicating the portion of training data. And the third one is changing the bias of an already trained model. Once we identify the list of killable mutations, we then check if these mutations are trivial. And by that we mean if any test set kills the mutant. Our motivations behind this question is that if the mutation operator with a given parameter is trivial, then it does not provide any useful feedback for the improvement of the test set because it gets killed by any test set. So to answer these questions, we use 4 different test sets. So the first parameter we used to create diverse test sets was the test suite size. So we took 5%, randomly sampled 5% from the largest available test suite, and then another test set, we used 50% of that data. The second parameter we use to create test sets is the confidence of the original system on the predictions that it makes for the test input. So we created one test set with high confidence input. So the original model is very confident on this input. Therefore, it would be hard for the mutation to misclassify them. And the second one is a test with low confidence. So the original model is already not very confident about this input. So it should be easier for the mutation operator to create misclassifications for these inputs. So in the paper, we report each operator and parameter pair, which is trivial for each subject. However, here I will give just a couple of examples. So if we apply remove data operator with a percentage value greater or equal to 75%, it becomes trivial for all subject systems, which is the same happens also for label error mutation operator if we apply it with a value of 50% or higher. So what happens here is that these mutation operators, they change a big portion of data. Therefore, the generated mutant gets killed by any test suite because it's very weak. So the second research question is a comparison with a threshold-based mutation killing. So we compare our statistical notion of killing to the most intuitive baseline, which is the threshold-based. So the idea here is that we see if the accuracy drop between mutated and original is less than a given percentage. So we use 3 different values for that percentage, 1%, 5%, and 10%. So when we apply our statistical notion of killing to 20 models, we get one answer for this set of 20 values, that this mutation is killed or not killed. However, for threshold-based, this value can vary from run to run as the accuracy drop can be different. So when we apply this experiment to the label error mutation operator for CIFAR, here on x-axis, we show the values of percentage with which the mutation operator has been applied. And on the y-axis, we report the fraction of the runs which are produce the killed mutation according to these threshold values. So we can see that as the mutation becomes more aggressive, the 1% threshold mutation killing says more and more often that the mutation is killed, but we also can see that for a given percentage across 20 runs, it produces different outcome for mutation killing each time. So here with 50%, we can say that for 30% of the runs, it says that the mutation has been killed, while for 70 it doesn't. And the same happens with the 5% threshold mutation killing. It says more and more often that the mutation has been killed, but it's inconsistent across 20 runs. And these results hold for various mutation operators and subjects, but here again, I just show one example. Our third research question is the comparison with syntactic mutations. So what we have done is that we used the MutPy, which is the mutation testing tool for Python, and it has 27 mutation operators that do syntactic changes. So for our 5 subject systems, it has generated 389 mutants, and again, each of them we have trained 20 times. Out of 389 generated mutants, for 68, the introduced syntactic changes prevents training process. So it removes or alters model.fit statement, for example, such that the training process doesn't take place. So these mutations are useless for any evaluation of deep learning models. Then 176 of these mutants causes failures. So this very often happens because the mutation tool reads the code and just sees some numbers and changes them. But it leads to the change in the input shape of a layer, for example, or it finds a text, which is the name of activation function, and replaces it with an empty string, so the code doesn't compile anymore. The remaining 145 mutations, though, were useful for our analysis because they did not cause failures or prevent training process, and out of them, only 50 were killable. So we performed a qualitative analysis of these killable mutants, and the only one operator that intersects with the list of the operators that we have analyzed that are specific to DL systems is remove layer. The other two change the normalization of data. Again, the tool sees numbers and changes them, but this affects the normalization of data, or it's like the number of epochs again is the number and the tool changes it. So this leads in a change of hyperparameters. So this results shows that when we use just a traditional mutation testing tool and a deep learning model, we get only 13% of mutants that are killable, and the big majority of them are useless for the evaluation of deep learning models, which confirms the need for DL-specific mutation operators and tools that would produce such mutations. So with this, I want to conclude the empirical evaluation that I present from our paper, and I want to address a couple of open challenges that I think exist in this field. The first of them is the correspondence of these mutation operators to real false. So the main hypothesis behind mutation testing is that if a test suite is able to detect mutants, then it would be able to detect also real faults. However, the mutation operators proposed in these 2 papers, they are not inspired or somehow obtained from real faults. So as there are now works that analyze real faults in deep learning systems, I think it would be interesting to get mutation operators from those faults and analyze their behavior on deep learning systems. The second open challenge is about the support in test suite improvement, because usually mutation testing is used to improve the test suite. So for example, if you change in your code plus to minus and you don't have a test case that reacts to that fault, you get an idea of what kind of test case you should add to your test suite. However, for deep learning systems, if you change a weight of your already trained model and you don't catch this mutation, what is the feedback that you as a developer get in the improvement of the test suite? So it's not obvious, and creating tools that would generate automatically inputs that kill mutations would be an interesting future work. And lastly, I want to address the elephant in the room, which is the high machine cost, which is associated with mutation testing in general, even for the when it's applied to traditional software systems, but as deep learning systems take usually long to train, this cost becomes much more. So whether this cost is worthy or not is an open question, and any cost-benefit analysis on this matter or any approaches that would reduce the cost of mutation testing as applied to deep learning systems would be of a great interest. So with that, I want to conclude my presentation. So today I talked about deep learning systems and their characteristics that requires them to have mutation operators tailored specifically to them. Then I introduced to you the statistical definition of mutation killings that we propose in this paper and showed that it provides more stable results rather than a threshold-based mutation killing. So thank you for your time, and now the live version of me should be there to try and answer your questions. Thanks a lot.